So yeah, there's the live stream now. Okay, so we're going to start today, Monday, with Professor Christophe Royon from Kansas University. He studied in France in École Normale Supérieure. I hope I pronounced that well. My French is not that good. His master was on quantum physics, and then he did a PhD at CEA Saclay and the University of Orsay. Royon's research helps advance in many disciplines by providing a better understanding of subatomic particles and their role in matter throughout the universe, harnessing the capabilities of colliders, atom smashing devices such as CERN LHC near Genova or Fermilab near Chicago. So, Christophe, the show is all yours. So you can go ahead with your talk.
So thank you very much. So before I start, I would like to thank, the organizers for the opportunity to give this presentation about the research that we are doing in Kansas. And also, I think for me, it's the first time, I'm giving a talk in Honduras. I've never been to Honduras physically, actually, but I think it's one of my goals is to develop definitely collaboration with Latin America. So going, from Mexico, I have collaborators in Mexico, also in Brazil, and so on. So I think we should have much more collaboration with Latin America, with the US, and also with France, since you know probably that I'm French. So that's why I think we need to enhance this kind of collaboration. So what I would like to discuss today is a kind of a description of what the proton is. So I will start by describing what is the Large Hadron Collider at CERN. Then I will discuss what is a proton, probably starting from the view that you might have of a proton, and we'll see that in fact it's more complicated than what you may think. I will discuss some strange events that were measured at the Tevatron in the US and now at the LHC, which are called diffractive events. I will mention a discovery in which I was part last year, which was the so-called odderon discovery. So I will explain, of course, to you what the odderon is. And I will finish by discussing something that we are doing nowadays, also at the LHC, is to look for what we call anomalous couplings, or also different ways for action-like particle or dark matter production using data at the Large Hadron Collider. So let me start with something which is very basic, which is related to the scales and the tools that we need in order to look for the constituent of matter. As you probably know, so the first thing that people used in history was the microscope. So with the microscope, you can look for cells, for the different cells that exist in nature. And for this, the typical size, a few tens of microns, like 50 microns. Then if you want to look at something which is smaller, like nanometers, you need a kind of electron microscopes that can reach the domain of DNA. And if you want to see something which is even more fundamental that we are doing in nuclear physics or in high energy physics, like to look at nucleus, which is the typical size is Fermi, which is 10 to minus 15 meters. Or if you want to look between quotes, because we don't look at them directly, as we will see, it's more the consequences. If you want to see something which is about the size of the quark, you need something which is 10 to minus 18 meters. And if you want to understand the structure of matter, the tools that you need to have is a particle accelerator. So there is a long history of people trying to understand what the structure of matter is. In fact, it started a long time ago, the concept of atom, which was coming from Greece, actually, so ancient Greece. And this is what people were calling atom, is something that you cannot break. This is what it means in Greek, actually. The word atom means something alpha, and tom, this is something that you cannot break. So for the Greek people, this was the kind of ultimate structure of matter. And in fact, we had to wait quite a long time. You see that the nucleus was discovered around 1910, so we almost waited 2,000 years, so that we understood that the atom has some structure. and especially that the atom is made of nucleus and electron. And the electron was discovered in the 1940s. And again, we had to wait more to see that the nucleus themselves has some structure, which is basically protons, as you know, and neutrons. And then the 1970s to discover the quark and the gluons, which are responsible for quantum chromodynamics. And then, so far at the LHC, so it was written 2010, 2012, but of course it's still taking data nowadays. So far, we didn't discover any substructure either for the electron and the quark. So as it is nowadays, these are the elementary forms of matter as we know them nowadays. So now I just want to discuss some energy units. So probably this is already familiar to you because you are a physicist, but I just want to give you a reminder because this is the kind of energy scale that we are going to discuss all the time during this talk. 1 electron volt is the amount of energy that is gained by an electron when it's accelerated by 1 volt battery, as it is shown, for instance, on this scheme with a 1.5 volt battery, as everybody has experienced it already. So we defined kilo electron volt, which is 4,000 electron volt, which is a domain of X-rays and TV. Mega electron volt, 10 to the 6, which is more the domain of radioactivity. Giga electron volt, the domain cosmic rays and accelerators, and even the domain of energy that we are discussing at the LHC, what we call TeV, or tera electron volt, which is 10 to the 12 electron volt, which is definitely the most energetic accelerators on the planet. And this is the domain of the Large Hadron Collider. So what is the Large Hadron Collider? So probably you heard about it already. So you know that it's located at CERN. So CERN is the laboratory which is just at the border between France and Switzerland. And there is a schematic which is here on and this basically located underground. The center of mass energy of this accelerator is now about 13, and we are starting to data 13.6 TeV, and the ultimate energy will be 14 TeV. The circumference is about 27 kilometers. As I said, it's located underground, between 50 and 100 meters underground, under, again, France and Switzerland. Just to give you some feeling, the energy per beam is of the order of 800 megajoule. And 1 megajoule melts about 2 kilograms of copper. The power consumption is about 120 megawatts, which is, let's say, the consumption per year of the middle-sized city, which is, for instance, I give you one middle-sized city in the US, for instance, Ann Arbor, which is of the order of 200 megawatt in 2008 as an example. So this is the kind of power consumption that we are talking about. So this is, you need quite a bit of power to run this accelerator. So why did we build the LHC? I mean, what was the motivation? And in fact, is to go back in time. The goal of the LHC is to be as close as possible as the Big Bang. So this is a kind of advertisement, I would say, which shows the age of the universe. So this is where we stand today on the right. And you see the different times of the universe, starting at times 0, which is the Big Bang. And what we would like to show you is basically the proton-proton collision and the heavy ion collision, because the Large Hadron Collider can collide protons and also heavy ions, are very close to the time of the Big Bang. This is just shown on this plot where you see the reference here, which is 10 to minus 32 seconds. This is where inflation ends, and 1 microseconds when the protons formed. And you see that basically the LHC is between these kind of two times. So we are very close to the time of the Big Bang. So we are close to reproduce the condition that appear at the time of the Big Bang. And this is also something which is fundamental because we can try to understand what is the structure of particle and also maybe to produce what we call particles beyond the standard model, which do not exist any longer today, but where might have been produced at the time of the Big Bang. So if I want to introduce the LHC, as I said, so we want to be very close to the time of the Big Bang. So in fact, you could consider that this is the hottest spot in the universe. In fact, when the two proton beams collide, they reach a temperature which is of about 10 to the 17 degrees, which is a huge temperature. Just to give you some feeling, the temperature in the sun is about 10 to the 7 degrees. So it means that you have 10 orders of magnitude between the temperature that we reach at the LHC and the temperature which exists in the sun. And this, of course, is very local. We don't have in a large area this kind of temperature. This is only at the point of the collision between the two protons. But still, this reproduces the conditions that are about 10 to minus 13 seconds after the Big Bang. So it's right after the universe was born, as I just mentioned. So in a way, you can say that this is definitely the hottest spot in the universe today. Then at the same time, which is a bit funny, the LHC is also the closest spot in the universe, the coldest spot in the universe. Why is it the coldest spot? It's because the LHC beams are kept in orbit using superconducting electromagnets. And these magnets, they operate at a temperature which is minus 271 degrees. So this is or 1.9 Kelvin. And I must say that it needs about 1 month to cool down the LHC, so it takes quite a bit of time to cool down the full machine. And it requires about 10,000 tons of liquid nitrogen and about 100 tons of liquid helium, just to cool it down and to keep it cool. So this is, you could say at the same time, the world's largest refrigerator. So what characterizes the machine furthermore? I mean, what is the goal of the LHC? So you imagine you have this collision between protons or between heavy ions, and you want to take a snapshot of what is produced during these collisions. So this is illustrated on this figure, which is here, where you see that in the middle, in the yellow area, there was a collision. Plenty of particles have been produced. We will come back to how do we measure this kind of the particles in the following. But you want to take a snapshot as if you were taking a photo of what happened during the collisions. So, in fact, the idea of the detector is similar to a digital camera, except that it had many pixels. It would be a 100 megapixel camera. And also that we are taking pictures very often. For instance, about 40 million pictures per second. So it's really a huge number of pictures that we can collect, a huge amount of data that we can collect at the LHC. And in addition, contrary to your camera, which is only sensitive to light, we are also sensitive to other types of radiations. So just to mention the two main experiments, so there are more experiments that we will discuss, also some result of one of them, which is called Totem, but there are two general experiments which are called the Atlas and the CMS. There are also two other big ones, which are called the ALICE and LHCb. But I just wanted to give you an idea of the size of these experiments. So for those who have already been in Mount Rushmore in the US, so this is a kind of a mountain, and in fact, they did some sculpture of some US presidents, and you can see the size with respect to the trees, which are also shown on the picture. So what I added on this photo is the size of the Atlas detector, one of the two experiments, a big experiment, and the CMS experiment on the right, and I am a member of the CMS experiment. So you see that these experiments have a huge size. Can you compare it to the size of the tree? And also, they are quite heavy, because even the CMS detector is about 30% heavier than the Eiffel Tower in Paris. So why do we need this kind of very big detectors? You may wonder, I mean, why do we need such a big monument, in fact, to measure the particles that are formed after the collision? So the idea of basically a detector, any detector at any colliders is always the same. What do you want to do is to absorb and measure all the particles that are produced after a given collision. The tricky part is that you need more or less material according to the kind of particle that is produced after the collision. So this is somehow illustrated on this plot, where you have, first of all, these are this kind of dotted or detectors which are close to the center, to the point of interaction. This is what we call a tracking detector. The tracking detectors allows to measure the tracks or the trajectories of the charged particles. Then you have another categories of detectors, which is here in orange. This is what we call an electromagnetic calorimeter. Another one, which is in blue, which is here an hadronic calorimeter. And this is due to the fact they are dedicated to measure different kinds of particles. As an example, the electromagnetic calorimeter, they can measure the photon, they can measure the electrons, and also we need more material, for instance, to absorb the protons and the neutrons. That's why you use an hadronic calorimeter. We can use, for instance, steel in order to absorb this kind of particles. So this is always the same idea. You have different layers because they are detected. They are dedicated to absorb different kinds of particles. The muons that are produced after interaction require even more material to be absorbed. That's why they are in the outer part. So this is this kind of bluish, grayish kind of detector that are at the end that allow to measure the muons. There are even some particles that cannot be absorbed, and this is the dashed line which is on the right, which are the neutrinos. Because probably you know that even the neutrinos, I mean, they can cross the Earth for most of them without interacting. So of course, they cannot be detected in our detector. So the way they are measured is indirectly because they will appear as some missing transverse energy inside our detector. So as I said, so we have a huge amount of data that is produced. So for instance, every year we would need about 2 million DVDs or 15 million CDs if we were putting all our data on CDs or DVDs. So the amount of data that we need to treat is really enormous. And that's why CERN developed what we call the grid. And the idea of the grid is to use any computers in the world that is free. For instance, in France, when I am sitting now, in a few hours, it will be night. So the computers will be free because the people will be away back home. In Honduras, you will still be working because you are 7 hours, there is 7 hour difference between France and Honduras. So it means that you could send some job on the computers in France, they will run on the computers in France, and when the job is finished, it will be returned to you, since the computers in France will be free. So this is the idea of getting a world grid, so all the computers are connected together and can analyze the data that are produced at CERN when the computers are free. So now let's come a bit about the physics, and we will see, first of all, what is a proton? So if I was asking, I mean, probably to a few students, what is a proton? You might tell me, okay, so the protons are definitely constituent of nuclei. They are quite small. As we said, the size is about 1 Fermi or 10 to minus 15 meters. And they are made of 3 quarks, which are 2 up quark and 1 down quark. So it's probably what you would have answered if I had asked you, what is a proton? And in fact, the vision I have of the proton is more the object which is in the bottom, not the object which is on the top. And you see that it's much more complicated. You still see the 2 up quarks and the down quark, but you see also these kind of strings which are gluons, which are the constituent of the protons. And you see also that there are many balls which are green and purple that correspond to what we call C quark, so some pairs of quark and antiquark. So this is more the vision of the proton that I have. So now let's discuss a bit about the proton structure, because the proton structure depends how we look at it. And it's quite a complicated object. And it appears differently according to its energy. And there is this diagram which corresponds to what we call Higgs, I mean the Higgs variable as physicists that correspond to 1 divided by the momentum of the quark or the gluons which are inside the proton. And on the horizontal axis, you have the resolving power, the variable that we call Q squared. So this is basically keeping the image of a microscope. This is the kind of resolving power of your microscope that you have to identify the internal structure of the proton. And the higher the energy of an accelerator is, when we have bigger machines, so for instance, the LHC, the biggest machine that exists in the world, the higher values of resolution or the higher values of Q squared that you can reach. So you are sensitive to more details inside the proton. So that's why when you have this kind of structure, when you increase the resolving power, the value of Q squared, you can see some more details. And when X, this variable, or 1 divided the momentum is increasing, you see that the number of quark or gluons, what we call partons, inside the proton can be very large. So this is this kind of image I just showed you before, where you have this kind of gluons, many gluons inside the proton, and you can even neglect these 2 up quarks and down quarks in this domain because they are their number is much smaller than the number of gluons and the C quark inside the proton. So this is why I was telling you, this is this kind of proton that we are more sensitive to when we discuss the proton at the Large Hadron Collider. So now let me give you a remark how we are analyzing data at the Large Hadron Collider. So as I said, when we use the LHC as a proton-proton collider, so you have collision between 2 protons, and what we are sensitive to, or what collides, in fact, are the objects that constitute the structure of the proton. So you can get a quark and a gluon colliding, or 2 gluons colliding, but of course, we do not decide what will collide inside the proton. So do we get something which is purely statistical? So our job is to take the data and then to try to understand what happened during the collision. We cannot tell the proton, please collect, we will collect only data where there is gluon-gluon interaction, or the gluon only should collide. Of course, this is impossible. So that's why we need to record many data and then select the data that are interesting for us. So this is what we do. And to do this, I want to probably remind you, you might have heard about it already, what is the standard model of particle physics? So as we said, we discussed a bit about the quarks. So there are 6 kind of quarks. So UD, we already mentioned, charm, strange, top, and bottom. So the top quark is the heaviest, and we will mention a bit about it in the following slides. And it was discovered at the Tevatron in the US about, I think, 20 or 30 years ago. I forgot exactly the dates. Then we have also 6 kind of leptons. So the electron, the muon, and the tau, and the neutrino, which are associated to this electron, muon, and tau. And there are forces, which are the kind of vectors that are responsible for the different forces. So what you know is electromagnetism, which is the photon. Then you might have heard about the weak force. There are what we call the Z and W boson. And then the gluon, which is the mediator for quantum chromodynamics, basically nuclear physics, or the interaction between quark and gluons that we are going to discuss mostly today. And everybody of you probably has heard about the Higgs boson that is responsible to create the mass of all the particles, and all what exists on Earth. So I just want to give you an example of an analysis to give you some feeling how it works. So this slide is a bit complicated, but we will go a bit in all the details, but just to show you how it works. Let's say that you want to measure one event. So again, you accumulated plenty interactions, and I want to work about the top quark. I would like to try to identify some top and anti-top interaction. So this TT bar interaction. So how I am going to select the events that correspond to top and anti-top interactions. So the only way to look at this top, so TT bar production, is to look at the decay of this top quark. And the top quark almost decay instantaneously into a W boson. I just mentioned the previous slide, this W boson, and also a B quark. Okay, this is good, and this is the same for my T bar, the W boson plus a B quark, which is here. And this W boson can decay in different ways, either into quark, so this is these 2 blue quarks that are here, or into a lepton and also a neutrino. So let's say I want to identify this kind of TT bar events in this kind of decay. So what I will ask in order to recognize these events is, for instance, 2 B quarks, what we call B jets that are produced in the detector, two light quarks, these two bluish quarks that are here, one lepton, which is measured in my detector, plus some missing transverse energy, which will be characteristic of the neutrino. So this is the way that we are going to select this kind of TT bar event. So you adjust the requirements of the particles that are produced in your detector according to the kind of events that you want to measure. So this is just to give you some feeling how the kind of analysis are working in high energy physics. So I want to introduce something which is maybe a bit tricky, which is the domain of saturation. And this is something that we are studying. So I'm sure you will have other talks about this kind of domain also by Louis, who is one of my PhD students, will give a talk on Friday. So I'm sure he will mention this and also some top events at the LHC. So what is saturation? Saturation, as I said, the number of gluons when this one over momentum, this famous X variable, the physicists call it, is getting very large. So what is happening? This is the same situation like when you are, for instance, in the metro in Paris at peak hours. The metro is very, people are very squeezed. It's very high density of people in the metro. And in that case, you can see that all these people are very close to one another. So what is happening is a kind of new phenomenon that is happening because if something hits or the metro breaks very fast, there will be a global movement of all these people because they are so close that one another. If there is something that happens, they will move together as a full entity. And in fact, this is the same for the gluon inside my proton. They are so close that you can consider them to be related between each other. And even at some point, they behave like a dense object, like a glass, what we call a color glass condensate. And this is this new behavior of a proton that we are studying at the LHC. For instance, how this kind of new behaviors can appear at the Large Hadron Collider. And this also implies that the usual equation of quantum chromodynamics that describe the interaction between the quark and the gluons are no longer valid. And there are new equations which are much more complicated that we need to test at the Large Hadron Collider and later on also at the Electron Ion Collider that will exist in the US. That has been recently decided. It will be built at the Brookhaven National Lab. So this is one of the topics that we are studying at the LHC, this kind of new phenomenon that we call saturation. There are other strange events, and this is, I will spend a bit more time on this, which are called diffractive events. And this is very special events, and we are seeing them every day at the Large Hadron Collider. And I will give you an analogy so that you could understand what is going on. So let's say that we have a collision or an accident between two large trucks. These are the two incoming protons and they interact. There is an accident between my two very high energetic protons. And after the collision, in fact, these two trucks remain intact and you can produce even some small car in addition. So this is exactly what we see every day at the LHC. You have a proton-proton collision and there is a non-zero probability to have intact protons after interaction, after the collision, and you can produce many additional particles that are produced after interaction and can be detected in the main detector. So what we did is to install special detectors that are able to measure this intact proton in the final state. So in fact, the protons are scattered at very small angles. That's why we put this kind of detectors very far away from the interaction point, to be sensitive to very low, very small angles in order to measure a great part of this intact proton in the final state. And as we will see, this kind of events led to the odderon discovery. I will mention in a minute what is the odderon, and also they lead to new kind of searches for extra dimension or action-like particle in the universe. So in order to introduce the odderon, let me start with what we call elastic scattering. Elastic scattering is like playing pool. I'm sure many of you, already played pool. So you know that when you play pool, you launch a ball against another, and there is some scattering between the balls. Of course, when we play pool, I mean, the balls are not destroyed and they remain intact after interaction. So this is the same kind of interaction that we study in high energy physics. For instance, two protons can go to two protons. So this is what we measure at the Large Hadron Collider. Or this kind of interaction can exist also between proton and antiproton. I will come back to this in a few slides. So in the same way as the pool game, so the protons, they remain intact, they are not destroyed, but they are scattered at some angles and they can lose or gain some momentum. So what we want to do is to measure this kind of interaction. So this slide is a bit technical, I mean, a bit more complicated, but I want to illustrate two things. So let's assume that we have two protons that want to collide, and what we call this kind of diagram is a Feynman diagram. What does it mean? When you are on the left, it means the particle before the collision. And when you move from left to right, this is when time evolves. So what we represent is kind of a complicated structure, represent the interaction, and at the end, these are the particles that are produced after the collision. So what I said, we want to measure elastic events. So this is basically the protons are intact in the final state. And I assumed on this drawing that one gluon is exchanged between my two protons. As I said, gluon is a kind of mediator. So this is how the strong force appears, is that one gluon is exchanged between my two protons. A gluon has a property to radiate many gluons. And if you have a single gluon which is exchanged, in fact, this diagram cannot exist. The proton will not be intact, they will be destroyed because there is some color exchange between the two protons. In fact, for the proton to be intact, you need a colorless object represented by this kind of string, which happens between the two protons. And from the quantum chromodynamics properties, in order to get a colorless exchange, you need at least two gluons. So there can be two gluons, three gluons, four gluons, five, and so on and so forth, but definitely not a single gluon. So this is when you want to get my two protons, like in the pool game, and nothing else which is produced, you need at least two gluons that are exchanged between my two protons. So, and this was the goal for this slide, was to introduce a bit what is the odderon. So the odderon is a bit a complicated object, as I said. So we are interested in this elastic event. So I am starting with two protons, and I have, like in the pool game, I have my two protons in the final state and nothing else. When you are playing pool, you have two balls after the collision, and there are two balls and nothing more. That's exactly what we want to observe. And in fact, as I said, this object can be two gluons, three gluons, four gluons, five gluons, and so on. And in fact, that's why we introduce, I mean, it's one word, you can admit it as it is, what we call pomeron is made of a two gluon or an even number of gluons. It can be 2, 4, 6, 8, and so on and so forth. Whereas the odderon, like odd, is an even number of gluons that is exchanged between my two protons. So it can be 3, 5, 7, 9, whatever you want. And why do we introduce this fact is, in fact, because the probability to have some interaction between a proton-proton and a proton and antiproton, which is given here by this A pp and A pp bar, in fact is not the same. This is the sum of the even part plus the odd part when you have proton-proton interaction, and the difference between the even part minus the odd part, so the odderon, for the pp bar interaction. So I know that it can be a bit abstract for you, I mean, a bit complicated for you in this kind of explanation. But what I want to stress, and this is immediately, is that the probability of interactions, proton-proton going to proton-proton, like in the pool game, when we collide two protons, will be different from the elastic interaction between proton and antiproton. This is just what I want to remind for these two very simple formula, is that if the odderon exists, if this term is not zero, you expect some differences between proton-proton and proton-antiproton interaction. And this is exactly what we looked at to have the evidence of the odderon. So as I said, so the proton-proton interaction at the LHC, so the proton-antiproton, in fact, this was the Tevatron. It's already a collider that I mentioned before that was located close to Chicago in the US. So at that time, it was the highest energetic collider between proton and antiproton. So it went about 2 TeV, so exactly 1.96 TeV. And I was, and I'm still, member of the D0 collaboration. So what tools do we have to measure the intact proton and the intact antiproton in the final state? Are what we call Raman pots. Raman pots is a very simple idea. I mean, why is it called Raman? It's because the first detectors were built by the Rom group, I mean, a long time ago. And why a pot? Because it looks like a pot. So you have a drawing on the left, you have the beam, which is just here in the middle of the beam pipe, which is here. And the idea to measure this intact proton that are scattered at a very small angle is very simple. You just want to have a detector that can move as close to the beam in order to measure the protons scattered at a small angle. And why they are scattered at small angle? Because they have lost a bit of their energy when they interacted. So what we do is when the beam is not stable, when you inject the beam, we put the detectors a bit far away so they are protected. And when the beam is stable, when you want to detect the scattered proton, you move the detectors as close as possible to the beam. And when I am talking as close as possible, it's up to 3 sigma from the beam. So it's really very, very close to the beam. So just to show you some photos, so this is this kind of detector that I just mentioned. So the beam is horizontal line, and this is this kind of bellow, which allow to move the detector close to the beam. And this is on the right, where you see these detectors inside the tunnel. I mean, it's maybe a bit difficult to see. They're in the middle of the green rectangles, because you see that it's quite busy in the tunnel with all the cables. So what do we do? In order to measure elastic interaction, we just count the number of events that are as a function of a variable that we call T. T is the quadri-momentum transferred square at the proton vertex, and we can measure this by tracking the protons through the magnets. So I will not enter into the detail, but this is basically the way that we can measure this kind of number of events as a function of T, and we can do this for all the different center of mass energy that we have for the accelerators. So as you see in the previous slide, there can be some structure, for instance, some minima and maxima that can be observed in this kind of measurements. And you may wonder, why do we see this kind of maxima that we call bumps and the minima that we call dips? And it's probably some experiment that all of you did, I mean, in optics, and we see the same in high energy physics. In optics, when you throw a laser through a slit, you have a diffractive pattern that appears. So you see some maxima, again, maxima of the intensity. And this is exactly what you observe, this kind of view, when you have the maximum in the middle, and then you have some maxima and minima of the intensity. And this is exactly the same that happened in high energy physics. So what we did, first of all, we measured elastic proton-antiproton interaction. So this is illustrated here by the D0 collaboration. So you have this famous d sigma dt as a function of t, and the data points are the black triangles. Then we did the same at the Large Hadron Collider, and this is what I mentioned. This is TOTEM, which is an experiment close to CMS that I mentioned. And these are the different measurements that were performed at different center of mass energy of the Large Hadron Collider, 13, 8, 7, and 2.76 TeV. So what do we need to do? If you remember, I mean, our idea that we had at the beginning is to compare between PP and PP bar interaction. But we need to have some data at the same center of mass energy if we want to compare the data directly. Unfortunately, Tevatron is at 1.96 TeV, and the LHC is at 2.76, 7, 8, and 13 TeV. So if we want to compare both data sets, we need to extrapolate the LHC data down to the Tevatron energy. And this is what we did. In order to do this, we identified some kind of characteristic points of the behavior of the elastic cross-section as a function of T for different values of energy. What you see, since they're all, you see all these data that are presented for different square root of S, and they always show the same pattern. At low values of T, the data, the cross-section are decreasing, you reach a minimum, then you have a maximum, and they decrease again. Whereas if you compare it to PP bar, we don't see this kind of pattern. There is a decrease of the number of events, and then it's more or less flat. So this was the general idea how to compare between proton-proton and proton-antiproton data. So that's why we identified 8 characteristic points of the behavior of elastic PP interaction. I will not go into the details, but I will mention that 2 which are obvious as the minimum that we call the beep and the maximum that we call the bump. And then we choose some region which has the same number of events as the dip, but at higher T. We took also the points which are in the middle between the bump and the dip. So we identified some kind of 8 reference of characteristic points of the shape of elastic proton-proton interaction. And what we did, in order to predict what is the shape of the PP elastic interaction at the tevatron energy, we fitted all these characteristic points in T and number of events down to the tevatron, center of mass energy, as you might remember, is 1.96 TeV. And this led basically to the discovery plot that is shown here, which compares the PP bar measurement in blue, so this is the measurement by the D0 collaboration at the tevatron, compared to the extrapolated data coming from the measurement by totem at the Large Hadron Collider, which are the red triangles. So you see immediately that there is some difference between the 2 data sets. You see that definitely these points here are incompatible. So the difference was explained by the existence of the odderon. As we mentioned before, the natural way to have difference between PP and PP bar interactions is the existence of the odderon. And the difference was estimated to be about 3.4 sigma. It was combined with previous measurements that led also to some evidence of the odderon. And if you combine it, it leads to a significance which is larger than 5.3 sigma. So it led to the discovery of the odderon, which was performed last year. So now let me come for the last part of the physics I want to discuss briefly. As I said already, is that the same kind of events where protons are intact in the final state are also sensitive to beyond standard model physics. As you know, we are sensitive also by this method by looking for extra dimension, because extra dimension might exist in the universe. You know that the usual dimension in which we are living is 3 + 1, so 3 dimension for space and 1 for time. But it may be that especially gravity lives in higher dimensions. And how are we going to look for this kind of events? And you may remember, this is again looking for the events where we have intact proton in the final state, is by gamma-gamma or light by light, since a photon is of course light by light interactions. So in this kind of events, you see that again, this is the same kind of diagram. So time is going from left to right. There are some real or quasi-real photons that are emitted by the proton. They are emitting light. We have some light by light interaction, which is a pure quantum effect. Of course, I mean, in standard model, in classical mechanics, this does not exist. Light doesn't interact with light, so it's a pure quantum effect. And we can produce some photons in the final state. And these photons are sensitive to extra dimension in the universe. There can be also other particles that can be produced. I already mentioned W or Z boson, or also TT bar events that can be produced in this way. So I just want to do a small parenthesis, in fact, because this will be the complexity for this kind of analysis. In fact, when there are protons colliding at the LHC, you should not think as one proton colliding with one proton only. In fact, we collide packets of protons. And there are millions of protons that collide at the same time, or within the same bunch crossing at the LHC. So there is this kind of events that we just mentioned, where you have two protons that collide, and then after interaction, you have two intact protons plus two photons. But something like this can happen, where you have two intact protons, but also you see that two photons, and they are originating from different interaction between two different proton interaction. All these kind of stars represent different proton-proton interaction. And on this small diagram, and I only showed you 6 interactions, and you should imagine that there can be up to 50 proton interaction, what we call pileup, at the same bunch crossing at the LHC. So we need to distinguish between these events that are clearly background and these events that are clearly signal that we want to keep. And this is where measuring the intact proton in the final state is very important. Why is it like this? Because you see, in the case that the protons are intact in the final state and we measure the two photons, we measure all the particles that are produced after interaction. It means that, for instance, the angular distribution of the two protons and the two photons will be the same. Or in other words, you have conservation of energy. You know that energy and momentum is conserved in physics. It's a general property of physics. And that's why, since we measure all the particles of the final state, we can apply the conservation of energy and momentum on this proton system and the two photon system. So this is why the mass of the two proton system and the mass of the two photon system will be equal for our signal, whereas for our background, since my two photons have nothing to do with my two protons, they will be different. And this is the same for the angular distribution. This is illustrated on these two plots, which show the mass ratio between the two proton system and the two photon. Signal is in black, and this pileup background in red, and the same for the difference in angular distribution, signal in black and pileup background in red. So you see immediately that the fact that we measure all the particles allow to be sensitive to this kind of new coupling between four photons in an unprecedented way. So using this kind of method allows to improve the kind of search for action particle or extra dimension of the universe by 2 to 3 orders of magnitude compared to other methods at the Large Hadron Collider. And this is something that I proposed about 10 years ago. And this is now reality. I mean, now we have already the first sensitivities at the Large Hadron Collider in CMS. So the measurement and running this forward proton detector at high luminosity at the LHC was possible with the effort of the full collaboration. So just to show you some sensitivity, so this is photon-photon going, for instance, to action-like particle, also decaying into photons. So this kind of coupling photon-photon to action, which is here, versus the mass of that particle. And this is the kind of sensitivity that we see in the grayish area. So we gain about 2 orders of magnitude in mass of the action and sensitivity. And also we have a domain that is not covered at the LHC, which is even at higher mass of the action-like particle. So what I would like to finish in maybe in the 10 last minutes is to discuss very briefly a way to get rid also on this background. Another method is to measure the time of flight of the proton. Again, when you have this kind of very interesting, you remember two photons and they originate from the same interaction that produce my two protons. And these events that we want to remove because in fact they correspond to different interactions. So the idea would be to measure very precisely the time of flight of the proton so that we can ensure that this proton originates from the same interaction that produce, for instance, my two photons. And for this, we are developing kind of detector that allow to measure the proton time of flight with high precision. Let us discuss the order of magnitude of precision that we need to measure the proton time of flight. So in everyday life, so you have, for instance, this rabbit that you see that everyday life, he has a watch. And typically the watch that you are using is sensitive to hours, minutes, seconds, maybe fraction of seconds. But these are the kind of time scale that we have for our everyday life. And we use, of course, watches and clocks for that. So can we use this kind of standard detectors for our proton? In fact, not. So let's have a kind of order of magnitude. And I want just to discuss very briefly some experience that all of you had in the past already. So when there is a thunderstorm, I mean, what you see, first of all, is the light of the thunder. And then after a few seconds, you hear the thunderstorm. You hear the noise of the thunder. So why is it like this? It's because for the light, as you know, the speed of light is about 300,000 kilometers per second. So it means that in 10 picoseconds, so or 10 to minus 12 seconds, in 10 picoseconds, particles travel 3 millimeters. Whereas for the speed of sound, which is much slower, we have about 343 meters per second. So it means that's why we see the lightning before we hear it, because of course the speed of light is much higher than the speed of sound. And the protons that we have at the LHC, they are almost at the speed of light, 99.99999% of the speed of light. So it means that if we want to have some resolution, which is of the order of millimeter, we need this kind of precision of the measurement of time, which is picosecond kind of precision. So definitely your watch will not be enough. So that's why we developed new kind of detectors, which are called silicon detectors. And we reach, this plot is a bit old already, using fast silicon detector, about 40 picoseconds per layer of silicon detector. We are more closer to 20 picoseconds now with using this ultra fast silicon detector. And we use them, in fact, by developing a new method to analyze the signals. The idea is very simple. So you measure the signal inside the silicon detector, and it's rather a fast signal. It's just a few nanoseconds. We start by amplifying the signal. So we designed a new amplifier at the University of Kansas to amplify without modifying the good properties of the signal coming from the cyclical detectors. And then we do a very fast sampling of this signal. It means that we measure, for instance, you see here, decreasing part of the signal. We measure different points of the value of the signal. These are these yellow crosses. And how can we reconstruct the arrival time of the signal is by doing some linear interpolation between these different crosses. You see, using this method with a signal which is about 2 nanoseconds, you can get a very good timestamp when the signal arrives in the detector. Using the same method, you can also reconstruct very precisely the amplitude and the shape of the signal. So this is the method that we use to get the time of arrival of our protons. I just want to mention that we are using, in fact, the same method to measure cosmic ray in space. So I will be very brief, but the idea is to use the same kind of detector, and we are going to send our detectors in space with NASA, so it's collaboration with NASA using a CubeSat, in order to measure the particles that are in cosmic rays, if they are proton, helium, iron, lead, and at the same time their energy. So what we do to do this, we measure the signal using the same method when the particle stops in a given layer of the silicon detector, what we call the Bragg peak. And using the same method, we can reconstruct the full shape and amplitude of the signal, which is directly related to the kind of particle and also their energy. So the other method that we used, and we just got, in fact, approved by National Institute of Health in the US, so they will start this in more detail, is to measure doses when people are treated for cancer. So using exactly the same method, we can count the number of protons that have been absorbed when people are treated for cancer, and in that case, know exactly the dose that has been submitted to the people. And it is very important when you use flash beam. So this is very intense beam that are used to treat the people and to some tumors, like for instance in the brain. And as far as we know, we are the only people that are able to measure precisely the dose during this kind of treatment, which are new treatments that are appearing nowadays to treat some tumors, again, for cancer. And just to illustrate this, we put our detector in the University of Dublin in Ireland in order to measure the structure of a beam that is used to treat people. And for the first time, we were able to see the bunch-to-bunch structure of the beam that is used to treat the patient. So this was the first time that it was observed in a signed medical accelerator. So I just want to conclude now. So we discussed a bit the Large Hadron Collider, which is the highest energy collider in the world. It led to the Higgs boson discovery. You heard about it. I didn't mention it because probably you had some presentation already about it, but I mentioned the odderon discovery that happened last year. And it could bring many more unexpected results. As I mentioned, extra dimension, action-like particle, which would change the way we see the world. And in addition, I mean, this will be a bridge between high energy physics or particle physics and also kind of astrophysics, a large domain in cosmology. We use these fast timing detectors also and for applications, like many applications in medicine or also in cosmic ray measurements. So I only mentioned two in which we are involved at KU. As an example, measuring doses received during cancer treatment. I just want to show you to finish a small cartoon. So basically you see that these people are in a safari in Africa. They are looking for definitely for animals, but they are not looking in the right direction and they do not even see the lion who is sitting just in the back. So we should not do like these people, but we should look for everything at the LHC and we should look everywhere. We already discovered the Higgs boson and the odderon, and who knows, maybe we will see many new things again at the LHC with the data that are being taken now. So thank you very much.
Okay, great. Thanks you, Christophe, for this really, really clear and nice talk. We're just on time, so that's great. So we have time for a couple of questions. If anyone on the audience wants to ask a question, maybe you can raise your hand and I can give you permission to turn on your mics. So, and if someone on the in-person room wants to ask a question, you also can. I don't know if anyone there.
Yes, questions from students.
Yeah, questions from students are the best. Well, maybe meanwhile I can ask a couple while there's there's Brian there. So
go ahead.
Oh, okay. Yes, I have a couple of questions. First of all, this just a very little one. Maybe it's a little bit dumb, but I'm not sure. While you were talking about the extra dimensions, this with the intact protons, you mentioned that the photons that are produced as quasi-photons. What do you mean with that a photon is a quasi-photon?
A quasi-real photon. In fact, because in high energy physics, there could be what we call quasi-real photon or the virtual photons, which we put a star, in fact, in high energy physics. It means that, for instance, this is just an exchange particle. So it doesn't need to be a real particle that is emitted. In this case, it's really light that is emitted. But this is, in theory of high energy physics, that you can exchange particles that are not on their mass level, let's say. So that's why there can be virtual particles that can be exchanged. And I didn't discuss it in more detail. Maybe it's a bit abstract, but it's the way it appears when we discuss this. In fact, the fact that we can access this low mass domain and so on, it also using this kind of events is due to the fact, or the very high mass domain, that you can produce some particle in a virtual way, even outside their mass domain. And again, we represent this in high energy physics by putting some stars that are here to indicate that they are not really produced. It's because, in fact, again, they are exchanged between the two photons, or before between the protons. So they don't need to be real particles that are emitted and absorbed. If you can see what I mean without going through the theory or more complicated formula. Is it okay? Or
yeah, that's
a bit tricky to explain.
That's totally great. Yeah. Another thing that I wanted to ask, now that you mentioned cosmic rays at the end, I was wondering, of course, cosmic rays reach very high energies,
Yes.
bigger than what we can have with an accelerator.
Yeah.
So do you think it is possible maybe in the next couple of years? I know it's hard to direct collisions with cosmic rays, but do you think we can use cosmic rays in such a way that we can do fundamental physics with them? Like study this kind of phenomena, how viable can it be? Is it really
Yes.
hard? Do you have an idea?
Yeah, I think that definitely, I mean, it's extremely interesting to study this, especially this very high energetic cosmic ray, and to try to understand how they are produced. So and this is still difficult nowadays. I mean, to understand what produced these extremely high energetic cosmic rays. So it's still a mystery. The only difference we have between high energy physics and the cosmology is that cosmology, of course, you cannot act. I mean, you need to wait until these high energy cosmic rays are produced, and then you can observe them. Whereas what we do in high energy physics is like to produce this kind of events. We accumulate million and million and million of events in order to understand what is the interaction, which interaction occurred. But of course, I mean, with the present accelerators, by far, we cannot access these huge energies that appear in cosmic rays. So that's why they are complementary. We need both this kind of high energetic cosmic ray that are produced, and we need to try to understand them in a better way, and at the same time to have some experiments in order to understand better how the particles are produced, with which kind of interactions and so on. Just to give you an example, for instance, we use also models to describe the high energy cosmic rays, so extrapolated from the LHC energy, and we tune this kind of Monte Carlo models to the LHC data, to the LHC measurements, so that at least they can describe the particle production at LHC energy, and then they are extrapolated to higher energy of the cosmic rays.
Okay, so yeah, that was a great answer to my question. So thanks a lot. Now I give the word to Dr. Brian. So.
Okay, thank you, David, and thank you, Professor. It was really a nice talk. You were very clear.
Thank you.
I had two questions, but I think one of them was already answered. Professor, what can you tell us about, for example, supersymmetry or supersymmetric model from the experimental point of view? I mean, collider and astrophysical. Is the idea still feasible?
So this is a good question. I mean, the supersymmetry, as you know, I mean, it's a very nice theory from the theory point of view. Let's say it solves many problems or many issues with the standard model in a very clean way and nice way. But unfortunately, at least in the minimal supersymmetric model, it is rather disfavored. When you are at the minimal Sugra and so on, so far there is no evidence at all using the LHC data of any production of supersymmetric particles, as you might know. So in that sense, these minimal supersymmetric models are definitely disfavored, especially that in minimal model, you would expect this supersymmetric particle to be produced at rather small mass. But then if you go to more complicated model, which are not minimal model, then there is a lot of freedom in the parameter that you can put in supersymmetric models. So when you have that many parameters, it's clear that you cannot exclude supersymmetry, because if nature chooses a more complicated supersymmetric model where there are many free parameters, the only thing you can do as an experimentalist is to try different models, and you will put some limits on the value of these parameters. But you cannot say that supersymmetry doesn't exist. The only thing we could say is that minimal supersymmetry is rather disfavored. But if you go to extended version of supersymmetry, then it will not be possible to say that it doesn't exist in an absolute way. Maybe nature chooses something else, we don't know. So what we are missing nowadays to guide us in a beyond standard model physics in some clear signal that would say, okay, this is definitely not compatible with the standard model. So this is something that we are missing nowadays. Hopefully, we'll get something with the new LHC data or with future accelerators. Who knows? This will be really a push for our field. But still, as I was mentioning, many measurements, you know that we need to understand, for instance, the proton independently of beyond standard model physics. The LHC is bringing lots of data related to hadronic interactions. And hadronic interaction, we still need to understand many, many things, like I mentioned saturation, for instance. And this is something which is very interesting to study in addition to beyond standard model physics. So this is not the only topic to be studied at the LHC.
Okay, thank you very much. I think it's a
Thank
good
you.
idea for Susie.
Okay, great. Now we have a question from someone on the room, so you can go ahead.
Yes, thank you. So my question opposed to the other questions is more of something of logistics and technology. So my question is, are detectors in LHC run 3 powerful or precise enough to make significant advances in the study of these phenomenons, or should we wait for the construction of future accelerators like the FCC to get a better understanding or a clearer glance to the landscape? I mean,
so it's also a good question. So there are 2 things, because as you know, the LHC is moving to get higher luminosity. So this is what we call the high luminosity LHC with the same kind of energy. We will not change a lot. I mean, we move from 13.7 to 14, but it's not a huge change in energy. So there will be more statistics. So of course, the detectors, especially the triggers and the silicon detectors, will allow to measure more particles that are produced, because we'll get more interaction up to 200 pileup events per bench crossing. So with the new detector, we'll be able to analyze this kind of particles that are produced. So this is very good. But it means that also that, for instance, in the run that exists now, if we don't see beyond standard model events, it's not because you multiply the luminosity by 3 or 4 that you will get some beyond standard model events that appear. So there needs already to be some excess in the data that are going to be taken now before the high luminosity LHC, if we want to see some new discovery that the high luminosity LHC, or new particles, I mean. So, and in parallel, as I was mentioning before, definitely these high luminosity events will allow us to measure some interactions or some hadron production that are rare, that we know they've already been discovered, but we'll be able to do some better measurement, more precise measurement. So this is not only a kind of discovery machine in that sense, but also a machine that can do precise measurement. And you were mentioning the FCC, for instance. So in fact, if we want to make discoveries, the important point is to get a higher energetic machine. So then you are sensitive to higher mass, object of higher mass that can be produced. So this will be the next big opportunity. Of course, it's not for tomorrow. I mean, first of all, it has to be decided. It's very expensive. So it's kind of a world project, because it cannot be just one nation who can build this. So, and also, so it has to go through the building of the machine when it's approved. So unfortunately, it's not for tomorrow, but probably 20 years from now that we can get the FCC. So I would say definitely we need to use fully the LHC for both the searches with the data that we are going to accumulate now, and also precise measurement that we can do with the LHC. And again, we know, who knows? I mean, maybe in the 3 years, there will be some hint of something that is still not expected with the higher number of data that we can take at the LHC, because many measurements that we have today are still limited by statistics. So increasing the luminosity will allow to get more precise the measurement by increasing the statistics of this measurement. So does it answer a bit your question?
yes, thank you, Professor, that
Thank
answer.
you.
Yeah, thank you.
Okay, Christophe, if you have time for a couple more participations, we have, I don't know. Yes. So we have another raise hand, but yes, I think we're a little bit off the hour, so maybe we can. Thanks, Professor Royon, for.
And so if people want to send me some question by email or something, I mean, you should not hesitate. Yes.
Yeah, we have a Slack channel, so if you want to join, if you want to join, we could send you the link by email. And
yes, that's good.
Yes, then you can join, and maybe if if it's good to you, you can provide to us the slides of the presentation.
Yeah, of course. I can send it to you by email or yeah. Mhm.
Yeah, okay. So we'll send you an email with this Slack link and yes, and remind about the slides. So thanks a lot for your time.
Thank you. Thank you
And
very much, and thank you again. Thank you very much for the invitation and the opportunity to present the results. Thank you.
Thank you, Professor.
thanks a lot. I have a couple of questions, so I'll ask by Slack. I'll be there.
Thank you.
Okay,
Thank
okay.
you.
Very great. Thank you, Professor. See you.
See you, and I hope it will be the beginning of a new collaboration with Honduras. I mean, I would
Yeah,
be very happy.
Yes,
Yeah, for
we'll
sure.
be. You will be extremely happy to collaborate. Yes, and we have a direct contact with Luis, so
Yes,
he can
exactly.
be he can be a mediator for
Yeah, an
for
entry
further
point.
call. Yeah.
Thank